Hello everyone, myself Nisha Rani, lecturer physics, gsss chak, Jalandhar district, Punjab. Today my topic is kinetic theory of gases. In this we will discuss about kinetic theory of gases, its assumptions, derivation of pressure exerted by a gas and root mean square speed of gas. First of all, what is kinetic theory of gases? The kinetic theory of gases actually describes a gas as a large number of submicroscopic particles such as atoms and molecules, all of which are in random and constant motion. The randomness of these molecules arises from the particles' collision with each other and with the walls of the container. As students, we know that the gas possess very negligible force of attraction between its molecules, and due to this, every gas obeys the following assumption. Number 1, the gas molecules are always in state of random motion. That means gas molecules are moving in all possible directions with all possible velocities. Number 2, due to their random motion, gas molecules always collide with each other and with wall of container. Next is, between any two successive collisions, molecules travel in a straight line with constant velocities. And then next, distance covered by molecules during the collision is called free path. Next, as the collision is perfectly elastic, the kinetic energy of molecules before and after collision is same. From all above discussion, it implies that gas molecules exert pressure on the wall of vessel. Before derivation, let us understand the concept of pressure. Pressure is the force per unit area. The basic formula for pressure is F upon A and SI unit of pressure is Pascal. Variation of pressure means it depends upon the amount of force, and second, it depends upon the area over which the force is applied. Now let us discuss about gas pressure. Gas molecules collide with the wall of the container and change velocity and momentum. The rate of change of momentum is force, and the force on the wall of the container creates gas pressure. The picture shows the pressure in the gases due to collision of molecules with the wall of a container. Pressure is proportional to rate of collision, that is, it depends upon number of particles, speed of particles and volume of container. What happens when number of particle increases? Actually, distance between particles decreases and thus more collisions occur, which increases the pressure within the container. And secondly, when volume of container increases, particles have more space to move around and thus less collisions occur and hence pressure decreases. Also, when temperature inside of container increase, particles gain more energy and move faster. The average speed increases and thus more collisions occur and hence pressure increases. Now let us derive an expression for the pressure exerted by gas molecules. For that, consider a perfect gas filled in a cubical vessel of side L as shown in the figure. Look at the figure, and by assumptions of kinetic theory of gases, the gas molecules are constantly moving in all possible directions with all possible velocities. Therefore, they possess momentum, thus exerts pressure on wall of the container. Let N, capital N, is the number of molecules of gas. Small m is mass of each molecule of the gas, and the total mass of the gas is capital M, which is equal to capital N into small m. Here A is the area, which is equal to length square, and that is L square. Similarly, V is the volume of the cube, which is equal to length cube, and that is L cube. Here rho, which is called the density of the gas, this is symbol for density of gas. This is equal to, as we know, m upon v. Rho is density is mass upon volume. Imagine that the gas molecules are moving in x, y, z coordinates axis with different velocities c1, c2 and so on cn. Let u1, v1 and w1 are the components of velocities c1 along x, y and z axis respectively. Therefore, c1 square is equal to u1 square plus v1 square plus w1 square. Similarly, velocities of remaining molecules can be given as c2 square is equal to u2 square plus v2 square plus w2 square, so on. For n molecules, Cn square is equal to Un square plus Vn square plus Wn square. Now, consider a gas molecule of mass m is moving along x-axis with velocity Un. Then its initial momentum is given by, initial momentum is mu1. The gas molecule will collide on wall of the container and moves in opposite direction with velocity minus u1. Since the direction is opposite, sign will be negative. Therefore, the final momentum of the gas molecule is minus mu1. Thus, the change in momentum of gas molecule per unit collision is equal to final momentum minus initial momentum, which is equal to minus mu1 minus mu1, thus equal to minus 2 mu1. Therefore, the change in momentum of gas molecule per unit collision is 2 mu1. Since the distance travelled by gas molecule during this collision is 2L with velocity u, therefore time taken by molecule during this collision is T is equal to 2L upon u, because time is distance upon velocity and molecule cover twice the length of the cube. Then, according to Newton's second law, force exerted by this molecule is given by F1 is equal to change in momentum divided by time. Therefore, F1 is equal to 2 mu1, which is momentum, divided by 2L upon un, which is time, and thus equal to 2 mu1 upon 2L u1. By cutting, we get F1 is equal to mu1 square upon L. Therefore, F1 is equal to mu1 square upon L. Substituting this as 3. Similarly, forces due to other molecules moving towards x-axis are Fz is equal to mu2 square upon L, and so on for n molecules. Fn is equal to mun square upon L. Thus the total force acting along x-axis is Fx is equal to F1 plus F2 plus so on Fn. Therefore, Fx is equal to m upon L u1 square plus u2 square plus un square. This is equation number 4. Now, by definition, pressure exerted by molecules along x-axis is given by Px is equal to Fx upon A. Since we already read that Px pressure is force upon area, therefore Px is equal to m upon L u1 square plus u2 square plus ua square, and area is L square, thus divided by L square, which is equal to m upon L cube u1 square plus u2 square plus so on un square. Similarly, the pressure exerted by molecules along y and z axis are Py is equal to m upon L cube v1 square plus v2 square plus so on vn square, and Pz is equal to m upon L cube w1 square plus w2 square plus so on wn square. But since pressure Px is equal to Py is equal to Pz, say P, therefore Px plus Py plus Pz is equal to 3P. From here, P is equal to Px plus Py plus Pz upon 3, or P is equal to substituting value of Px, Py and Pz. So P is equal to m upon L cube v1 square plus v2 square plus so on un square plus v1 square plus v2 square plus so on vn square plus w1 square plus w2 square plus so on wn square divided by 3. Therefore, P is equal to 3 L cube u1 square plus u2 square plus so on un square plus v1 square plus v2 square plus so on vn square plus w1 square plus w2 square plus so on wn square. Therefore, P is equal to m upon 3L cube c1 square plus c2 square plus so on cn square, as we already calculated that c1 square is equal to u1 square plus u2 square plus so on un square, and c2 square is equal to v1 square plus v2 square plus so on vn square, and for cn which is equal to w1 square plus w2 square plus so on wn square. Therefore, pressure is equal to m upon 3L cube c1 square plus c2 square plus cn square. For n number of molecules, pressure will be n into m divided by 3L cube c1 square plus c2 square plus so on cn square divided by n, where capital N is the number of molecules and m is the mass of the molecule. But since c1 square plus c2 square plus so on cn square is divided by n is the average velocity, that means pressure P is equal to m upon capital M upon 3V C RMS square, where capital M is equal to N into M, that is total mass of the molecules, and V is the volume of the cube, which is equal to L cube. Therefore, P is equal to 1 upon 3 rho CRMS square, where m upon v is equal to rho, which is the density, and density is defined as mass upon volume. So this is an expression for the pressure exerted by the gas when contained in a vessel. From above expression, average velocity square is equal to 3p upon rho. Therefore, VRMS is root of average velocity square, and which is equal to 3p upon rho. For an ideal gas, PV is equal to RT, as we know, where V is m upon rho, m is mass and rho is the density. So we can put the value of volume as m upon rho. Thus, Pm upon rho is equal to RT and Pm is equal to rho RT, or P upon rho is equal to RT upon m. Therefore, VRMS is equal to root of 3RT divided by m. Thus, root mean square speed of a gas molecule is defined as the square root of the average velocity squared of the molecules in a gas, and the kinetic energy of a gas molecule is affected by both molecular weight and temperature. Now, for better understanding regarding kinetic theory of gases, let us watch the next video.
Gas. It is everywhere around us, flowing through our atmosphere, encircling our huge planet, creating layers of gases covering the earth in vast square kilometers, buried deep beneath the foundations of the land that we live in, and finally running through the very air that we breathe. Unlike solids and liquids, gases are random groups of atoms that are spread out, and these atoms and molecules are full of energy. They are bouncing around constantly and can fill a container of any size or shape. Gas particles move in straight lines, being separated from each other, and they only change directions while colliding against each other or against the walls of the container. In this context, today we will discover one of the most important and fundamental theory of gases that help us understand its nature and property more clearly. This theory is referred to as the kinetic theory of gases. Before we analyze the theory any further, we should first have a basic understanding of kinetic energy. Kinetic energy is defined as the energy of motion. Any object has motion, irrespective of a vertical or horizontal motion. This energy can be derived from any form of motion, ranging from vibrational, rotational to translational, that is, movement from one place to another. Keeping this in mind, along with the property of gases, the kinetic theory of gases will be a lot easier to understand. The theory basically describes the behavior of a gas in macroscopic terms, that is, in terms of properties that a person can directly observe and experience. The kinetic molecular theory of gases begins with certain postulates that describe the behavior of molecules in a gas. These are, first, gas consists of a collection of small particles traveling in a straight line motion and obeying Newton's laws. The molecules in a gas occupy no volume, that is, they are points. Collisions between molecules are perfectly elastic, that is, no energy is gained or lost during the collision. There are no attractive or repulsive forces between the molecules. Now, to be able to experience and see the theory in practice and also derive an equation for it, let us take the help of a demonstration to understand the theory and the assumptions. In the first instance, think of a single molecule rebounding backward and forward in a container. If the molecule freezes for a few moments, just before it hits the right-hand face of the box, the momentum of the molecule will be mv, where m will be its mass and v will be its velocity. If it rebounds elastically from the end of the box, its momentum will be mv, but in the opposite direction. Knowing that momentum is a vector quantity, change in momentum will then be mv minus mv, which is 2mv. Note that we are making an assumption that the collision is perfectly elastic. The next step is to calculate the force of the shaded green face. To do that, we need to know the dimensions of the box. So we give it length L, width W, and height h. The molecule will rebel from one end of the box along to the other, rebound there and then back again. In this time, it covers a distance of 2L. Since it has a velocity v, the time taken, that is, distance divided by speed, is 2L divided by v. Here again, we are making an assumption. The distance that the atom or molecule actually covers is slightly less than the full length of the box due to its own size. So, we are making the assumption that the diameter or size of the atom or molecule is insignificant. Neither are we making any allowance for the time of collision. We are assuming that time is absolutely negligible. When the particle hits the side of the box, there is a force on the face due to the reversal of the momentum of the particle. Based on this, we calculate the average force on this face, which is equal to the rate of change of momentum, that is, the change of momentum divided by the time taken. We have seen that the change of momentum is 2 mv and the time taken by the molecule or atom to travel in the box up and down again. We have already calculated that, and the time is 2L over V, which results to mv squared over L. The average pressure of the phase, thus, will be force divided by the area, that is, force mv squared over L divided by the area, which is width into height, that is, WH. This gives us mv squared upon L into WH, which is the volume of the box. We then replace L into W into H with a capital V denoting volume. Now, we do expect a large number of molecules in the box, all going backward and forward. But we can't really point out the numbers exactly. So, we will simply give it the symbol capital N. In this way, the force on one phase due to n number of molecules bouncing backward and forward will be n into mv squared over v. Also, the molecule will not be just moving sideways. They will be going up and down and backward and forward. Since there are 3 possible directions in which they can travel, the average force therefore will be divided by 3. Considering the general assumption that the molecules have similar effect in every direction, we are particularly assuming that there are large number of molecules and that their motion is entirely random. This proof relies upon the molecules traveling in uniform speed and in straight lines, even when there are large numbers. We are assuming that there are no forces at all between the molecules to disturb. We have moved on to the point where we have a general expression for the motion of gas in the box. This expression implies that the pressure in the box is equal to the number of particles into the mass into the square of the velocity divided by 3 times the volume of the box. The kinetic theory of gases, thus, is a very critical element in understanding the nature of the gases and their molecules. Those gases which lurk within us, from the labyrinths beneath us to the world around and above us, encircling us with their energy.